Hello and welcome to the online seminar of ROHM's Next Generation Silicon Carbide MOSFET. In this presentation, let me first introduce the background of silicon carbide power semiconductors and the market status. Next, we will look at the technology and products developed by ROHM. We will focus on our latest 4th generation trench MOSFET and its performance. I will also discuss our new package options for improved efficiency and compact system design, as well as the costs and benefits of silicon carbide power devices, which often drives the decision to choose silicon carbide or the traditional silicon solutions. At last, we will summarize with a few takeaway messages. Silicon carbide is a compound semiconductor material with a wide energy bandgap. Compared to silicon, it is capable to withstand 10 times higher electric field before breakdown, making it an ideal material for high-voltage power switching devices. Silicon carbide power devices have been under extensive research in the past 30 years, and now the technology is delivering the promise of superior performance and making a big impact on power electronics design. So if you are working on power systems with transistors and diodes rated at 600 volt or higher, it will be a good idea to consider silicon carbide options to help improve your energy efficiency, increase switching frequency, or make the thermal management easier. A few industries are leading the adoption of silicon carbide devices today. The solar inverters and energy storage systems, where increased efficiency could really help the energy harvesting. Companies running large-scale data centers try to minimize the energy waste and achieve their target power usage effectiveness. And one of the largest markets for silicon carbide, electrified transportation vehicles, where expensive battery packs are installed on EV drive systems. You don't want to waste that valuable electricity on the inefficient silicon power switches. Thanks to the diversity of application spaces, silicon carbide market is growing rapidly, and that is helping everybody to get the product at lower cost. Starting from early years of this century, silicon carbide Schottky barrier diodes have been commercially available. The diode products experienced steady growth in power applications. More recently, challenges in the silicon carbide MOSFET fabrication process have been resolved, enabling commercial adoption of the power transistor in a wide range of market segments. Now and in the near future, the proven reliability and performance of the MOSFET is driving up silicon carbide demand in markets like the energy sector, electric vehicles, industrial equipment, and IT industries. With the latest technology options for high-voltage system design, these applications are becoming more energy efficient, compact, and environmentally friendly, contributing to a more sustainable society. To meet the strong market demand for silicon carbide power semiconductors in the coming years, ROHM is expanding our facilities for silicon carbide and gate driver production proactively. While today we are one of the largest producers of silicon carbide wafers and devices in the world, we will continue to invest nearly $1 billion to boost our silicon carbide capacity by up to 16 times towards 2025. This includes our substrate supply and the wafer processing capability. At the same time, the fab expansion currently underway for our gate driver products will increase the output by 15 times. Combining the advanced silicon carbide device technology and a high-volume, vertically integrated production system, ROHM will be able to offer power semiconductor products and system solutions with consistent quality and supply assurance. In the area of silicon carbide-based power devices, ROHM has been a leader of technology development and product commercialization in the past 20 years. Since 2009, we have integrated one of the world's leading silicon carbide substrate suppliers into ROHM Group companies. SiC, based in Nuremberg, Germany, now provides high-quality materials for our silicon carbide device production, as well as for other device manufacturers. After several successful launches of silicon carbide diodes, MOSFETs, and module products, we now offer a diverse portfolio of silicon carbide power semiconductors. ROHM has established 6-inch silicon carbide wafer process to secure the capacity for large volume production. This allows us to fully support the automotive and industrial customers. Later this year, we will introduce the 4th generation silicon carbide MOSFET products, which is the latest breakthrough in our silicon carbide technology. At this time, ROHM offers silicon carbide discrete products in 3 voltage classes and a wide range of current ratings. Our 2nd generation diodes are based on Schottky barrier structure and available at 650 volt and 1200 volt. The 3rd generation silicon carbide diodes use the JBS design to enhance surge current capability and reduce reverse leakage current. In our MOSFET products, both planar structures and trench technology are in production. While most of our products are 650 volt or 1200 volt class, we do support voltage ratings up to 1700 volt for higher voltage systems. For high power applications, such as automotive traction inverters, there is a need for silicon carbide devices of lower RDS(on) and higher current ratings. This will be supported by our next generation silicon carbide MOSFET with up to 5x5 mm die size. For most of our silicon carbide discrete products, a standard industrial grade option as well as an AEC Q101 qualified automotive part will be available. ROHM's silicon carbide MOSFET has evolved through a few generations, from the early planar gate design to the unique double trench structure offering much improved performance. With chip design and process advances, from the 2nd generation to the 3rd, we were able to reduce the MOSFET-specific on-state resistance by 50%. This means at the same die size, you will get much lower resistance during the conduction state and much lower energy losses. On the other hand, in most cases, you can use a smaller chip to handle the same power requirement, and that helps you reduce the cost. Our 3rd generation silicon carbide trench MOSFET is currently in mass production. And for the 4th generation, we will further optimize the trench design and bring down the on-state resistance value by another 40%. Now let me show some test data from our 4th generation research samples. This is the forward conduction performance data. With a chip size of 5x5 mm, a very low resistance of 12 milliohm is reached, giving it a higher current handling capability than the Gen 3 MOSFET of similar die size. The lower on-state resistance is a result of smaller cell pitch, better MOS interface, and additional process steps to reduce the substrate thickness. With the improvement of on-state resistance, better efficiency and lower cost can be expected. In this new generation products, it is also possible to drive the MOSFET with 15 volt gate voltage, like common silicon IGBTs. This could make it easier to replace the silicon device with silicon carbide. An important MOSFET characteristic is the temperature dependence of on-state resistance. Both our Gen 3 and Gen 4 silicon carbide MOSFET will have positive dependence from room temperature to the maximum junction limit, while for the new device, resistance ratio between 175 degrees C and 25 degrees C will be slightly higher. Essentially, this device behaves more like an ideal power MOSFET in theory, due to higher percentage of the resistance coming from the drift layer and less from the MOSFET inversion channel. These silicon carbide MOSFETs can be connected in parallel with good current sharing properties. For a normally off power switch like the MOSFET, a high gate threshold voltage helps keep the device off when 0-volt gate bias is applied during switching operation. ROHM designs our silicon carbide MOSFET with this target in mind. The threshold voltage of Gen 4 MOSFET has a negative temperature dependency, similar to Gen 3 technology, and the target value of threshold voltage is between 3.5 volt and 2.5 volt across the temperature range. With that, we can recommend using 0 volt to turn off the MOSFET without the need to provide negative gate voltages. Normally, when we improve on-state performance of the MOSFET, the saturation current at high voltage will also increase. As a result, a compromise in short circuit withstand time will be expected. This will not be the case for our Gen 4 design. In this device concept, a new cell structure is developed to suppress the short circuit current while on-state resistance is being reduced. This design ensures safe turn-off of the power device during a short circuit event. To compare the Gen 4 silicon carbide MOSFET with earlier products in short circuit conditions, we selected similar chip sizes and 2 silicon carbide modules were constructed and tested under the same short circuit event at 600 volt bus voltage. To help the understanding of the short circuit waveforms, it is useful to compare the high current, high voltage static behaviors of these 2 silicon carbide MOSFET. The left side explains how we characterized these 2 devices to high voltage and current, and the right side compares their behavior in the conduction state and the current saturation state. The solid black line on the right side chart shows the baseline Gen 3 behavior. As the blue curve of Gen 4 reduces conduction resistance on the low voltage side, it would be expected to have higher saturation current if technology remains the same. But because of cell structure optimization in the new double trench design, the saturation current is significantly suppressed to a level comparable to the baseline. With that, the trade-off between on-state losses and the short circuit capability is substantially improved. The actual short circuit test waveforms are compared on this slide. Saturation current for Gen 4 MOSFET remains below the level of Gen 3 during the short circuit event, and it also drops faster when the silicon carbide chip heats up. With similar chip sizes and lower short circuit energy, we can expect Gen 4 MOSFET to withstand the same or longer duration in short circuit events. In addition to the improvement in conduction loss and short circuit withstanding capability, we performed double pulse tests to analyze the switching loss performance. The devices are packaged into half-bridge power modules and compared side by side for 600 volt, 136 amp switching condition. No external freewheeling diodes are used, and the gate drive voltages are the same values for Gen 3 and Gen 4 devices. This slide shows the waveforms when the low side MOSFET turns on. DIDT slew rate is set at 8.1 kA per microsecond for both power modules, and we can observe a faster drain voltage fall time for the Gen 4 device. This difference can be explained by a lower Miller capacitance for the new device, which leads to lower turn-on energy losses even though the DIDT speed is not increased. When we look at the high-side waveforms of the same switching process, we will notice a lower recovery current for the 4th generation MOSFET. On the other hand, the rising voltage across the high-side device's drain and source terminals does not trigger a significant increase in its gate voltage for the Gen 4 MOSFET. This behavior is the result of a lower capacitance ratio between CRSS, which is the Miller capacitance, and CISS, the input capacitance. This feature is especially helpful to suppress parasitic device turn-on in fast DVDT conditions. And because of this, faster switching speed can be supported by Gen 4 MOSFET without the risk of shoot-through losses. We can find a similar switching comparison between the two-generation devices when the low-side MOSFET turns off. As the Miller capacitance is designed to be lower in Gen 4 MOSFET, faster DVDT helps reduce the turn-off losses. And because the DIDT slew rate remains the same for both Gen 3 and Gen 4 devices, the surge voltage across the drain and source terminals is not increased when we reduce the switching losses. This slide shows the summary of switching loss comparison. When the DIDT speed is the same for Gen 3 and Gen 4 parts, we will see faster voltage transition time for the new device. This difference can be explained by a lower Miller capacitance in the new chip design, which leads to lower switching energy losses even when the DIDT-induced surge voltage is not increased. The reverse recovery loss is also lower for the 4th Gen MOSFET, especially at higher switching speed. This improvement is the result of a lower capacitance ratio between CRSS, which is the Miller capacitance, and the CISS, the input capacitance. The optimized device capacitance helps suppress parasitic device turn-on during fast switching conditions and avoid shoot-through losses. Because of the significant reduction of total switching losses by chip design, high-frequency operation can be supported by Gen 4 MOSFET, enabling smaller power systems. To further optimize the switching performance on discrete products, we are introducing new packages to enable faster switching speed and less losses. Our traditional TO247 package uses one source pin for both power circuit and the gate drive connection. This makes the source stray inductance part of the gate drive loop. When the load current rises or drops rapidly, a voltage is created by LDIDT, which partially cancels out the voltage applied by the gate drive circuit and results in slower switching speed. With the new 4-pin TO247 and 7-pin TO263 packages, additional driver source connections are provided, and the gate drive loop bypasses the stray inductance of the main current path, so it can make effective control of the MOSFET switching speed. The benefit of the new discrete packages is clearly shown in the switching waveforms. Using the same silicon carbide chip but different package style, we are seeing a reduction of over 30% in switching losses by adding the separate Kelvin source connection, which can really help high-frequency operation with very little cost differences. The new discrete packages TO247 4-lead and TO263 7-lead are now available with the 3rd generation silicon carbide MOSFET up to 30 milliohm rating in 650 volt class and 40 milliohm rating for 1200 volt. These packages will also be offered with our upcoming Gen 4 MOSFET. For some applications where a smaller system size is important, we will be offering an alternative solution to the discrete building blocks. The SDIP package, which is a versatile platform to integrate several power devices in one module, is available now as design samples. We can put a full bridge or 3-phase bridge inside the SDIP package, and this can make the circuit board much smaller than using multiple discrete devices. And for power converters of 10 or 20 kilowatt power level, such as EV onboard chargers, the SDIP package can also be a more compact solution than traditional power modules for lower cost. These modules will include insulation on the backside by ceramic material, where heat sink can be attached. Now we have introduced the excellent performance and design options of silicon carbide power devices. It only makes sense to include these new semiconductors into your system design if the cost is right, and we know it is important for nearly any application. Silicon carbide is inherently a more expensive material to make than silicon, due to the crystal growth conditions, growth rates, special process equipment, and the not yet ideal defect density and yield rates. Nevertheless, in the past couple of years, the price reduction trend is accelerating, and now it is already the cost-effective choice for quite a few mainstream applications. The fundamental drivers of cost reduction can be market growth and productivity increases, larger wafer diameters, new technology and lower specific on resistance, and yield enhancement. ROHM is actively pursuing all these paths to bring down the cost for our customers, and we will help you create the most value out of silicon carbide for your power system. One example where silicon carbide MOSFET gets a lot of attention is the EV traction drive. Conventional EV inverters are powered by silicon IGBTs and PIN diodes. The cost of these silicon devices is competitive, and their performance at full load current is excellent. However, the vehicle rarely operates at full load. When the inverter is working at partial load current, the knee voltage of silicon bipolar devices will hurt the conduction efficiency. On the other hand, the slower switching speed caused by IGBT tail current and the diode reverse recovery will also limit the switching performance in the conventional silicon solution. Fortunately, now silicon carbide is available to solve the efficiency problems. With linear forward conduction characteristics and fast switching speed, silicon carbide can improve inverter efficiency by 3 to 8%, depending on the drive cycle. If we translate the energy savings into battery capacity reduction, we can see a perfect example where the more expensive power device can actually lead to cheaper and better power systems. Another application where silicon carbide can help improve efficiency and system size is the onboard chargers for EVs and plug-in hybrid vehicles. There are different topologies available for the charger design. It can be unidirectional or bidirectional, and we have seen customers evaluating silicon carbide for both the PFC section and the DC-DC converter stage. But by far, it seems the totem pole PFC circuit is a common example for silicon carbide MOSFET to play a big part in the system design. The topology eliminates inefficient diode bridges and utilizes power transistors in high-frequency, hard switching conditions. The transistor also needs a superior body diodes with low reverse recovery losses. Silicon superjunction MOSFET is not fast enough to fit the purpose, so naturally, silicon carbide MOSFET becomes a preferred candidate. The body diode of silicon carbide has very little storage carriers inside the drift layer, and switches nearly as fast as the Schottky barrier diode, making it ideal for the totem pole PFC stage. With higher switching frequency and a smaller inductor, the onboard charger can be made smaller. In addition to these EV applications, other industries like the IT infrastructure can also benefit from the silicon carbide power technology. Data centers are important for business and everyday life in the modern society, but they are actually big energy consumers growing at a rate that challenges the global energy supply. To mitigate this problem, governments have issued guidelines for data center power usage effectiveness, which measures the percentage of energy used by the computing equipment versus other purposes like cooling or power supply. The UPS system that data centers use are called online double conversion power supply because electricity is converted 2 times before reaching the IT equipment, no matter there is or there is not an electric interruption. This ensures the most consistent power delivery to the servers, but it does waste energy and generate heat in the conversion process. With silicon carbide, we can substantially cut the energy waste of the UPS, especially in light load conditions, improving the data center's power effectiveness and reducing the cooling burden, besides the possibility to also downsize the power supply system. Now we have talked about the status of silicon carbide technology, new products, and system design opportunities. Let me conclude this topic with a few takeaway messages. First, as the wide bandgap semiconductor industry develops a stronger supply chain, silicon carbide is clearly becoming attractive and competitive in automotive and industrial applications. The efficiency improvement and other benefit it brings to the system can often outweigh the additional chip cost. ROHM has a diverse portfolio of silicon carbide MOSFET and diodes, and we are offering new packages to optimize the switching performance of these devices. We also expect to release our 4th generation silicon carbide MOSFET in the next few months, with industry-leading performance and more competitive cost. We believe this will enable more and more high-voltage power systems to take advantage of the latest silicon carbide technology, with more benefits to gain and less price to pay. With that, I would like to thank everybody for attending this presentation. We look forward to working with all customers to discuss your application and provide assistance for designing with silicon carbide technology. Thank you.